Laser physics. It is the last chapter of second sem complementary physics. So today we are going to discuss about laser. What is a laser? A laser is a device that emits light through a process of optical amplification based on stimulated emission of radiation. It is the light amplification by stimulated emission of radiation. These radiations are in the electromagnetic. They are included in the electromagnetic spectrum. So their range, range of this radiations include in the electromagnetic spectrum. So they are nothing but electromagnetic wave. The light emitting from a laser is nothing but an electromagnetic wave, just like our light. But there are certain property for the laser. The first laser was built in 1960 by Thomas M. Myman at Hughes Research Laboratory, USA. He is both an engineer and a physicist. And the specialty of the laser is it is a highly monochromatic, intense, coherent, and unidirectional beam. We can say that it is a photonic device. It produces intense, monochromatic, coherent, and unidirectional beam of light. What is meant by monochromatic? Monochromatic means it will emit only single wavelength, a particular wavelength, or a wave with a particular frequency. So that type of wave is called a monochromatic wave. So it will have a particular color. It may be red, green, like that. It depends upon its wavelength. So we already discussed that this laser is an electromagnetic wave. So it has some energy, that is electromagnetic energy. It contains energy just like photons, just like light. Okay, this is also a light. So normally in the case of laser, the optical part of the spectrum normally extends from ultraviolet region to far infrared region, including the visible region. So this laser may emit, or the laser can emit even the infrared radiations, ultraviolet radiations, or ultraviolet. So it's a range from ultraviolet, visible, and infrared. Okay, but each laser beam has a particular frequency, but it may be in between, or its frequency in between this region. Okay, normally laser frequencies, or the laser frequencies lies in between these frequencies. Okay, anyway, a particular laser have a particular frequency. They are highly monochromatic. So this diagram shows its range. Here the far infrared to ultraviolet. This is here it is green color. It is neodymium, and YAG for yttrium aluminium garnet. So it is called ND YAG, normally called ND YAG laser. Okay, this is carbon dioxide laser. Another one is femtosecond. Yttrium is yttrium fiber laser. Okay, so these are the lasers shown here. So some applications of lasers are, it is used in medicine. We know the bloodless surgeries. We are familiar with eye surgery using laser, laser healing, and in industrial purpose it is used for cutting, welding, material heat treatments, etc. In defense also it is used for making targets, missile defense, and also it is used for sensors. In research, it is used for spectroscopy purposes. There are a lot of use for lasers. especially in non-linear optical studies. There are laser scanning. All these are used in research. And in commercial purpose, we know that laser is, we use laser printers, CDs, barcode scanners, etc. So in the aesthetic purpose also, we know that laser light shows, okay, water shows using the laser beams. So these are the applications of laser. So it has a wide range of application. So only a certain class of solids or gases, or it may be a liquid, may show this lasing property, or it normally used for making lasers. Normally, this impurity doped semiconductors and non-interacting gases like helium and neons are used for making lasers. So of course the energy structure of atom is responsible for these type of properties of laser. So we have to understand the energy levels and the energy transitions phenomena related to this process. So there are different type of interactions that taking place inside the atoms or in between the energy levels. Let us discuss about the interaction of light with matter. The three important phenomena that come under this type of interactions are induced absorption, spontaneous emission, and stimulated emissions. So these are all depends upon the number of atoms per unit volume. So all this depends upon how many numbers of electrons are present in a particular energy level of an atom. So for the lasing action to take place, the light have to interact with the material medium. Of course, it have a discrete energy level. Actually, the proper or total phenomenon can only explain with the help of quantum mechanics. We know the quantum mechanics is beyond our limit, so we will tell about the theory of laser in a simple manner. Actually, that is not the theory. We can only explain the full theory of laser with the help of quantum mechanics. Actually, we are not dealing with quantum mechanics in your classes. We can discuss the surface theory of laser. And we know that what is a radiation? Radiation is nothing but the flow of or continuous flow of photons, especially the electromagnetic radiation. Here we are dealing with the electromagnetic radiation. We know that light is an electromagnetic radiation. It contains quantas of energy, and the field particles which is responsible for these light interactions are nothing but photons, and photons carries an energy which is given by h nu, where h is Planck's constant and nu is the frequency of the light. So let us discuss what is an induced absorption. As its name indicates, it is something induced. So in order to induce which thing will induce this absorption? So that is a photon. So suppose we have an electron which is in this ground state. Normally this having energy even or initial state or even. Suppose even is the ground state or any other state. And when a photon whose fall upon this electron, it will absorb that photon or that energy, this photon containing energy h nu, and it will jump into the higher energy level, that is E2. And this after absorbing a photon, the electron jump from lower energy level to higher energy level, and this process is known as induced absorption. Okay, why it's called induced? Because it induces, this photon induces, and it is absorbed by this electron. So it is called induced absorption. The electron absorbs the light, and this electron should have an energy which should be equal to the energy difference between these two levels. That is the condition. Then only these electrons can excited to the higher energy state. The energy of the photon should be exactly same as h nu is equal to E2 minus E1. Okay, so this process is known as induced absorption. Next one is spontaneous emission. Spontaneous means it is not spontaneous, it is a natural thing. It is not influenced by any other external agent or any other external photons or anything like that. Okay, this spontaneous process is it's happened without any external agent. Here the atom is in this case the atom is in the excited state. Suppose there is an electron in the excited state. It is came down to the, we know that the excited state is not a stable state. So in order to acquire more stability or in order to lower its energy, the electrons come down to the ground state. As a result of this, extra energy is emitted, and h nu, that is exactly equal to E2 minus E1, is emitted, and this process is known as spontaneous emission. Here there is no external photon or anything like that. So this is a spontaneous process, and that is an emission process because an energy is emitted. Electromagnetic energy, which is equal to h nu is equal to E2 minus E1, is emitted. So it is an emission. So it is a spontaneous emission. Okay, that is a process which is called spontaneous emission. And the third process is nothing but a stimulated emission, that is responsible for this laser action, light amplification by stimulated emission of radiations. Here the electron which is in the excited state, and suppose a photon of energy is energy which is exactly equal to E2 minus E1 is absorbed by the these electrons, and as a result this extra energy and photon energy is emitted, that is h nu h nu h nu h nu. H nu is the excited electron energy. After the excitation it is emitted and the electron is go back to the ground state, and this energy that is coming from the external agent h nu, so 2 h nu is released during this process. So here this process is taking place with the help of an external agent or with the help of an external photon, and so that is called stimulated. Something is stimulate this process, so that is called a stimulated emission. So here photon is emitted due to stimulated process. Normally this process is taking place if the electron have a larger time period in the excited state. So in stimulated emission, an electron in the excited state need not wait for spontaneous emission of photons. Suppose a photon have energy E2 minus E1 interact with the excited electron at the energy level E2 before spontaneous emission take place. Then the excited electron at the energy level E2 make a downward transition to the energy level E1 by releasing 2 photons of energy h nu. This process is called a spontaneous emission. Okay. And one important property for producing laser is population inversion. It is one of the important property to achieve lasing action. So a laser will work only if there is a population inversion. Okay, what is population inversion? Population is nothing but the number of electrons present in each energy level. Population inversion means something happened away from the normal state. So that is inversion. Normally there are some there is some populations of ground state and population of excited state, but inversion means which is not normal. something happen inversely. So it is called population inversion. Suppose let us examine a material medium has two energy levels. Let E1 and E2 are two energy level. E1 is the ground state level and E2 is the excited state level. So the electrons are distributed differently in these two energy levels. Suppose N1 be the populations of the E1, that is ground state, and N2 is the population of excited state. Normally, this material at thermal equilibrium, or which is at equilibrium, at that process, the number of atom present in each level can be find out from Boltzmann's law. We know that from the Boltzmann's equation, N1, the number of electrons present in the ground state, N1 is given by e raised to minus E1 by kT, and N2 is given by e raised to minus E2 by kT. Here E1 and E2 are the energies of ground state and first excited state respectively, and K is the Boltzmann constant, and T is the temperature in Kelvin. So we know that N2 by N1, the population of the excited state by population of the ground state, is given by, when we do this calculation, we will get N2 by N1 is equal to e raised to minus bracket E2 minus E1 divided by kT. So what will be the value of N2 by N1? Normally, the electron will occupy in the ground state than the excited state. The normal tendency of electrons are to occupy the lower energy level. So that can be proved from this Boltzmann's expression. Okay, we know that E2 is the energy of the excited level, E1 is the energy of the ground level. So E2 minus E1 is always a positive quantity. So E2 minus E1. Normally the value of E2 minus E1 lies about around 2 to 10 electron volts. Or, exactly, sometimes it may be 2.0506 etc. electron volt. And the value of kT is around the 0.026 electron volt or anything like that. Normal, depends upon temperature, even though its value is very low. So when we substitute here, this is an high value. When you compare this with kT is very low. So when denominator is very low, the number is very high. So the e raised to minus, suppose this is approaching to infinity, e raised to minus infinity, it is nothing but 0. That means N2 is 0, or the higher energy state is have less population, or theoretically 0 populations. Okay, so N1 is more populated than N2, and that's why normally at thermal equilibrium the lower energy state or ground state is more have more number of electrons than the excited state. This is the normal condition. So that is the normal population conditions of an atom. Okay. So the distribution of atom among the energy level is termed normal distributions. So when N1 is greater than, very greater than N2, we will say that it is a normal state or normal energy or population distribution. In that state, there will be more absorption than emission, because the lower energy state is more populated. So there is a chance for more absorption than emission. So the condition for emission is that there should be a large number of electrons in the higher energy state. So in normal distribution conditions, number of electron in the lower energy level is greater. So there is no chance for an emission or any stimulated emission. So in order to because lasing action is nothing but stimulated emission of radiation. So in order to get a stimulated emission, the higher energy state should be more populated than the lower energy state. So that condition, if the higher energy state is more populated than the lower energy state, that is an inverse of normal distribution. So it is known as population inversion. That is, if the excited state is more populated than the lower energy state, it is called a population inversion. So the population inversion is a non-equilibrium state of material in which population of higher energy level N2 exceeds the population of lower energy level N1, and this is known as the population inversion. So once again, if thus the population inversion is a non-equilibrium state of material in which population of higher energy level, here it is N2, exceeds the population of lower energy level N1. So population inversion is nothing but simply if the excited state is more populated than the ground state or lower energy state, we call that as a population inversion. So here, this is the normal state. In lower energy state is more populated than higher energy state. So when they absorb photons, the excited state, so this higher energy state is more populated than this lower energy state. So it is a population inversion condition. This condition is known as population inversion condition. So then only there will be stimulated emission of radiation. This is stimulated emission of radiation if there is more population in the higher energy state, that is population inversion is achieved, that the the photon is spontaneously emitted. As a result, electron is de-excited to lower energy state. As a result, this radiation, this is the production of laser. So here laser light is produced. So laser light is produced when excited or higher energy state is more populated than the lower energy state. As a result, there will be, as a result, what happened? There is a chance for population, there is a chance for stimulated emission, and stimulated emission is responsible for what? Laser production. So that is a very simple way to explain the laser production. So there may be different levels of energy diagram. It is a 4-level laser energy diagram, 1, 2, 3, 4, or anything like that. This is 3-level. Here, this is excited level from the ground state. The electrons are excited to higher state. As a result, there will be more populations in the excited state. Sometimes, suppose here there are more populations in this level. ഇത് സംഭവിക്കുന്ന സമയത്ത് excited state number of populations കൂടും. ഈ ഇലക്ട്രോൺസ്, അതായത് ഗ്രൗണ്ട് സ്റ്റേറ്റിന് ഇലക്ട്രോൺസ് അപ്പർ ലെവലിലേക്ക് പോകുന്നു. പോയി കഴിഞ്ഞതിന് ശേഷം ഈ ഇലക്ട്രോൺസ് ഒരു മെറ്റാസ്റ്റേബിൾ സ്റ്റേറ്റ്, ഈ ലെവലിനെ നമ്മൾ കാണുന്ന മെറ്റാസ്റ്റേബിൾ സ്റ്റേറ്റിലേക്ക് ഇലക്ട്രോൺസ് ഡീഎക്സൈറ്റ് ചെയ്തിട്ട് ഈ മെറ്റാസ്റ്റേബിൾ സ്റ്റേറ്റിലേക്ക് വരുന്നു. ഇതാണ് മെറ്റാസ്റ്റേബിൾ സ്റ്റേറ്റ്. ഇത് നോർമലി അങ്ങനെ ഒരു സ്റ്റേറ്റ് ഉണ്ട്. നമ്മൾ നോർമലി പറയുന്ന പോലെ ഗ്രൗണ്ട് സ്റ്റേറ്റും എക്സൈറ്റഡ് സ്റ്റേറ്റും അല്ലാതെ ഒരു സ്റ്റേറ്റ് ആണ് മെറ്റാസ്റ്റേബിൾ സ്റ്റേറ്റ്. അപ്പോൾ ഈ മെറ്റാസ്റ്റേബിൾ സ്റ്റേറ്റിൽ എന്ത് ചെയ്യുന്നു? ഈ ട്രാൻസിഷൻ, അതായത് ഹയർ എനർജി സ്റ്റേറ്റ് എന്ന് ഈ മെറ്റാസ്റ്റേബിൾ സ്റ്റേറ്റിലേക്കുള്ള ട്രാൻസിഷൻ നോർമലി റേഡിയേഷൻ ഇല്ലാത്ത ട്രാൻസിഷൻ ആയിരിക്കും, നോൺ റേഡിയേറ്റീവ് ട്രാൻസിഷൻ ആയിരിക്കും. ഓക്കെ, this is known as the radiationless transition or non-radiating transition. അപ്പോൾ എങ്ങനെ ഇത്തരം ട്രാൻസിഷൻ ഉണ്ടാവും? ഇവിടെ എനർജി എക്സൈറ്റ് ചെയ്യണം, ഇതിന് കറസ്പോണ്ടിങ് ആയിട്ടുള്ള എനർജി എക്സൈറ്റ് ചെയ്യല്ല, എമിറ്റ് ചെയ്യണം, പുറത്തേക്ക് എമിറ്റ് ചെയ്യുന്നു. ഈ എനർജി എന്ത് ചെയ്യുന്നു? ഹീറ്റ് എനർജി ആയിട്ട് പ്രൊഡ്യൂസ് ചെയ്യുന്നു, അല്ലെങ്കിൽ ഈ എനർജി എന്ത് ചെയ്യുന്നു? ഈ ആറ്റത്തിനെ വൈബ്രേറ്റ് ചെയ്യിപ്പിക്കുന്നു. ആസ് എ റിസൾട്ട് ചെറിയ ഹീറ്റ് ഇഫക്ട്സ് ഉണ്ടാവുന്നു. പക്ഷെ ഇവിടെ എന്തുണ്ടാവില്ല? ഫോട്ടോൺ അബ്സോർപ്ഷൻ ഉണ്ടാവില്ല. അപ്പോൾ ഈ ഈ മെറ്റാസ്റ്റേബിൾ സ്റ്റേറ്റിലേക്കുള്ള ഒരു ഇത് നോർമലി നടക്കുന്ന ഒരു പ്രോസസ്സാണ്. ഇത് ഫസ്റ്റ് ലെവലിൽ നിന്ന് ലോവർ ലെവലിലേക്ക്, ഈ കേസിൽ ഫസ്റ്റ് ലെവൽ മീൻസ് എക്സൈറ്റഡ് ലെവലിൽ നിന്ന് ലോവർ ലെവലിലേക്ക് എന്ത് ചെയ്യുന്നു, ലേസർ എമിഷൻ കാരണം ലേസർ എമിറ്റ് ചെയ്തുകൊണ്ട് ഇലക്ട്രോൺസ് ലോവർ എനർജി സ്റ്റേറ്റിലേക്ക് ജമ്പ് ചെയ്യുന്ന ഒരു കേസാണ് ഇത് പറഞ്ഞത്. എല്ലാവരും അങ്ങനെ ആവണമെന്നില്ല. ഇൻ certain cases there is a chance for another state which is known as metastable state, and the reason is that the period of the lifetime of electron in the higher energy state is lower. ഈ പ്രോസസ്സ് നടക്കുമ്പോൾ സപ്പോസ് ഈ ഹയർ എനർജി സ്റ്റേറ്റിലെ ലൈഫ് വളരെ ഷോർട്ട് ആണെങ്കിൽ അവിടെ ഒരു ലേസർ പ്രൊഡക്ഷനുള്ള ടൈം കിട്ടില്ല. അപ്പോൾ അതൊരു മെറ്റാസ്റ്റേബിൾ സ്റ്റേറ്റിലേക്ക്. So that metastable state, let us discuss in the next slide. Okay, so one important thing is that, so in order to excite the electrons from the lower energy state to higher energy state, we have to provide some energy to the medium. Then only the electron from the lower energy state the electron in the lower energy state can excited to the higher energy state. Okay, here this is lower energy is more populated. So after absorbing some energy, that is in the form of photon or any other form of energy it can absorb, then only it can reach the higher energy state. Then only the population inversion is achieved. So to transfer atom from lower energy level to higher energy level, energy must be supplied to the medium. This process of supplying energy to the medium to achieve population inversion is called pumping. If we use an optical instrument, or if we provide it through a photon, we can call that pumping as an optical pumping. Okay, and the general process is known as pumping. There are several methods of pumping, that is optical pumping, electrical discharge, and direct conversions are some example for them. In optical pumping, as we discussed, a light source is used to illuminate the medium to achieve population inversion. So the energy from the light source is absorbed by the electron and it is excited to the higher energy state in order to produce population inversion. So normally it is adopted in solid state lasers. In electrical discharge method, the electric field causes ionization. Because of this electric fields, because of an electric field is applied to the medium, and that energy is used to excite. That energy is electrical. There is a field. As a result, these ions get accelerated if that is a gas. Okay, as a result it will get energy, and this energy is used for excitation process. So the electric energy causes ionization of the medium and raises this electron to the excited state. Okay, this is another type of pumping, that is known as electrical pumping. Normally in semiconductors lasers, direct conversion of electrical energy into light energy is taking place. So that are these pumpings are the method to attain the population inversion. So this is another term related to laser action, that is pumping. It may be optical pumping or an electrical pumping. Okay, so this is an example for population inversion. This is normal distribution. In the excited state where only small number of electrons. Here by absorbing energy, this is population inversion. So here this is in the excited state. There are large number of electrons than the lower energy state. So this is a population inversion. In metastable state, there are normally the metastable state are excited state of sometimes it may be atoms or ions. Suppose the medium contains atoms or ions. This metastable state is an excited state. okay, which have a relatively long lifetime than the normal excited state. So the metastable state, in metastable state, this electron can stay for more times, around 10 raised to 5 10 raised to 5 times extra uh, than the short-lived uh, excited state. Okay, so so metastable state, the higher state must be a metastable state, a state in which the electron remains longer than the usual time, so that the transition to the lower state occurs by stimulated emission rather than a spontaneous emission. If the time period is very small in the excited state, so if the time period is very small, it cannot undergo the stimulated emission. Only stimulated emission can produce this laser action. Okay, so in order to produce a stimulated emission, the electrons should stay more time in a state, in an excited state. In certain cases, the excited state are very short-lived. As a result, these electrons cannot undergo stimulated emission, but they undergo spontaneous emission. So this spontaneous emission cannot produce a lasing action. Only a stimulated emission can produce lasing action. So the state which should have a longer lifetime is called the metastable state. Here, this is the excited state. First, the electrons are excited to the higher energy state. But after that, it will undergo a non-radiative transition to a state in between the excited state and the ground state. That state is known as metastable state, that have a longer lifetime, so that the electron can stay in the metastable state for long time. Okay, so it can undergo stimulated emission. So that state is known as the metastable state. So this is the state. So normally this process, the excitation from the metastable state to the ground state produces laser. So here this is, and radiation is coming, have an energy that is E2 minus E1. So as a result of it, the electron will absorb the energy, and it will as a result these radiations are emitted. This is the coming radiation, and the energy difference between these two is also emitted. So this is a more intense radiation. So this is the laser rays that is coming out from this state. So this transition is known as the this transition is a stimulated emission, and this will produce a laser beam, and that is the importance of a metastable state. So next, let us discuss about types of laser. Laser can be classified into different classification, but we can here we can discuss one type of classification. It is based on the material medium or the lasing medium. Depends upon the lasing medium, the laser can be classified into three types, that is solid state laser, gas laser, and liquid lasers. So solid state laser, gas laser, and liquid lasers. An example for the gas laser are helium-neon laser, argon, krypton, xenon ions, nitrogen, carbon dioxide, carbon monoxide, etc. are the example for the gas laser. Here the medium is a gas, helium-neon, argon, krypton. Thus, normally inert gases are used, nitrogen, carbon dioxide, etc. are the gas example for gas type lasers. Next one is solid state laser, ruby laser, ND-YAG laser, ND-YLF laser, neodymium glass lasers, YB-YAG lasers, example of solid state lasers. An important example is, one of the important example is ruby laser. Okay, another type of laser is liquid laser, and dye lasers are used as a liquid laser. Here the natural dyes which is solved in a solvent is used as a lasing medium. So these are the three type of lasers based upon its material medium. Okay, there are a lot of classification for lasers, but according to your syllabus you have to study one type of classification. So let us discuss about ruby laser. It is an example for solid state laser. So ruby laser is a solid state laser that uses synthetic ruby crystal as a laser medium. Mayman in 1960 fabricated the first laser using the ruby crystals. The wavelength of the light that is emitted is in the visible region, and it is about 694.3 nanometer. And the important parts of a ruby lasers are, we know that in order to work a laser, it should have a lasing medium, it should have an resonator or the optical resonator, and it should have a pumping source. And this ruby laser is consisting of a cylindrical crystal rod of ruby. It's about 4 centimeter in length and 0.5 meter in diameter, whose ends are flat, and one of which is completely silvered and other one is partially silvered. So this is a ruby rod, and this is flash lamps, and there are two ends for it. This is two ends. One is completely silvered and other one is partially silvered. The silvered end thus form the resonant cavity. The ruby rod is placed inside an helical. This is the helical photographic flash lamp filled with xenon. So it is called the xenon lamp. So this is an helical photographic flash lamp, and it is filled with the xenon gas. So it is called the xenon lamp. Okay. So here the lasing medium is aluminium oxide doped with chromium. It is chromium. It is doped with chromium, which is the active material in ruby laser. Some mistakes are there. So here the aluminium oxide doped with chromium is acting as a lasing medium here, and this actually the chromium ion is the active material for the production of this lasing light. Here the excitation taking place for chromium ions. The electrons of the chromium undergo excitation, and as a result of this stimulated emission, it will produce this laser. Okay, light. The optical resonator, which are parallel plates, there are two parallel plates, they are silvered. Okay, and the pumping source here is the helical photographic flash lamp filled with xenon gas. So this is an optical pumping source. Okay, so it is known this type of lamp is known as the xenon lamp. So this is the construction of a ruby laser. Using this way the ruby laser is constructed. So let us discuss about the working of ruby laser. So this xenon lamp will provide energy to excite the electrons in the chromium atom. So the ions of these electrons of chromium ions undergo transitions. Okay. So when the flash lamp is switched on, the xenon discharges and generate an intense burst of white light lasting for few milliseconds. The chromium 3 plus ions are excited to an energy band E1 and E2 by blue and green component of white light. Here, if the ground state absorb this, sorry, there's a change in the picture. So this is the picture. So this is the picture. Sorry for the change in the figure. So this is the energy level transition of a ruby laser. So this is the ground state. This energy is absorbed from the xenon lamp. A green light and a blue light is absorbed. As a result, the energy is, as a result, the electron is excited to higher energy state. So when the electron in the ground state absorb the blue light, which is more energetic than the green light. We know that VIBG or violet have most energy because the frequency of violet is higher than any other. VIB, so blue is have higher frequency, so it have more energy. So when it absorb the blue light, it will excited to higher energy state. This is the one energy state, and this is when the electron in the ground state absorb the green light, it will excited to another energy level. That is, this is E2 and this is E1. Okay. So and this and we know that the time period in these two states is very low. The time period or the time period in these two levels are very low. As a result, there is no chance for spontaneous emission. So they are de-excited to in another state which have a more lifetime, and that state is known as metastable state, and the electrons are de-excited to this metastable state by transferring its energy to the lattice or to the another atoms. Anyway, it is by non-radiative transition, because there is no radiation is coming out or no energy, no light is produced during this transition. Okay, as a result, the electron is de-excited to the metastable state, and from the metastable state, the electrons are de-excited to the ground state. So this light output is, light is coming out which have an wavelength of 694.3 nanometer, that is red light. So this is the laser output. So this ruby laser produces red light. That is the this why the ruby laser is working. That is the working principle behind the ruby laser. Okay, let us examine other gas laser. Helium-neon laser is a gas laser. Ali Jawan and his co-workers fabricated the first gas laser in 1961. It is helium-neon laser, and the wavelength of light emitted from this is 632.8 nanometer. It is also in the range of red region of visible light. And important part, we already discussed about different parts, and here the lasering medium is nothing but the helium-neon mixture, gas mixture. The gain medium of helium-neon laser is made up of a mixture of helium and neon gas contained in a glass tube at low pressure. The partial pressure of helium is 1 millibar, whereas the neon is 0.1 millibar. So here the active medium is helium-neon gases, mixture of helium and neon gas. And the optical resonator is two parallel mirrors. These two mirrors are silvered, and here in both end they are silvered, but this what is but both are not silvered in equal amount. One side is more silvered, but other side is partially silvered. Okay, so these two mirrors are silvered, they, or we can call that as a optically coated. And the pumping source here is not an light source, it is an high voltage DC power supply. So it is used as a pump source in the helium neon laser. That is the basic difference between the ruby laser and helium neon lasers. These are changing in the case of a, there are a lot of change in the case of a helium neon laser. This is a picture of a diagram of an helium neon laser. These are the two mirrors. This is totally reflecting one or highly polished. This is partially polished and partially reflecting one. And this is the active medium. Here there are helium and neon mixture is there. These are electrodes. There are two electrodes, positive and negative electrodes, and it is connected to a power supply. And this is the laser production. These are the important parts of a helium neon laser. So the working, when the power is switched on, the discharge takes place inside the tube. So this is the tube. When the power switched off, the discharge takes place inside the tube. The electrons and ions produced in the process of discharge accelerated towards the respective electrodes. Okay, the energetic electrons collide with helium atom and excite them into higher energy level. In this process, the discharge take place and it collide with the helium ions, and as a result the electrons of helium is excited to the higher energy level. This will represent the excitation of helium electrons in the helium ions. Okay, here the electrons are excited to the higher energy state by colliding with electrons produced due to the process of this discharge, electrical discharge. This atom excited to the ground state, these electrons are de-excited to the ground state by colliding with the neon atom. So they collide with the neon atom and exchange its energy with neon. So these are the energy levels of neon. So they transfer the excess of energy to the neon through the collision. As a result, the neon atom are excited to the energy levels E4 and E6. E4 and E6 represent the energy levels of neon. So both of them have approximately same energy. This excited state of electrons of helium and the excited state electrons of neons are comparatively same energy. So here these two are the metastable state. Here by emitting the radiations of 3.39 micrometer, it is excited into E5, and by emitting the radiation of 6328 angstrom, it reaches the level E3. So here also the radiation is emitted and this will produce a laser. So this is another production. This transition is also produce a laser beam of 1.15 micrometer. So these are the working principle of a helium neon laser. Thank you.